Hi. We're going to be going over special quadratics. Types of quadratics that are pretty unique, and if you can spot their form, you can easily factor them. And they have to do a lot with perfect squares, right? Numbers that, are squares of another number, right? So like 3 squared is 9, or 16 is 4 squared, right? These numbers can be really, really helpful in factoring quadratics. And I'll give you an example of why. Say we're asked to factor, let's say, 9x squared minus 4. You're just asked to factor that. And that, first off the bat, looks really, really crazy. There's no middle term. There's no, plus 5x, for example. There's just an x squared, and there's a constant. It looks really, really, really weird, and we're supposed to factor this. It seems pretty tricky. What we notice here is both 4 and 9 are perfect squares. 4 is 2 squared, and 9 is 3 squared. We actually notice a very interesting relationship. This is equal to 3x squared plus 2. It's 3x squared minus 2. And we think that because we say this middle term is gone. Something has had to happen in this factoring, in this multiplication, to cancel out this middle term entirely. So we start thinking opposite signs. And the reason why I thought opposite signs is this. I'll show you. Let's say we're going to distribute out this big equation, right? We make sure we multiply each term by every other term. So we're left with 3x squared times 3x squared, that's 9x squared. 3x squared times negative 2, that's negative 6x. Oh, this should be x. That's negative 6x. Right? 2 times 3x, that's 6x, positive 6x, and 2 times negative 2 is negative 4. Now we notice, hey, we have a negative 6x and a positive 6x. That means these x's are to cancel out. We'll just be left with 9x squared minus 4, which is exactly what we have in our original equation. Now this property, where we have, the same thing but we split the signs, is actually what we call the difference of squares. And it's tremendously useful in helping us solve problems. Because if we see, a problem where, there's no middle term, we immediately think difference of squares. What squares am I dealing with and how did I solve it? So in general, right, if you have, perfect squares, ax squared minus b, where a and b are perfect squares, right, your factored form is going to be square root of a times x plus square root of b times square root of a times x minus square root of b. It's going to be that format. And that is very, very important to note, because if you spot any equation that looks like that, where you're dealing with two squares, and you're only dealing with two squares, you have two terms, you immediately think, can I use the difference of squares? Is this number here a square, and is this number here a square? Because if so, I instantly know just the factorization of that number. Now, squares will come up again, and this time in a slightly more complicated way, in what we call the sum and difference of squares, right? So say I'm given a number like, a quadratic like, x squared minus 10x plus 25. And I say, hey, 25, that's 5 squared. Maybe this is a perfect square. Maybe this is something. So I think, well, what would happen if I'm squaring something like x minus 5 or x plus 5? What would happen if I'm doing that? So I'm squaring that. I'll square these both, and I'll expand them out just so we can see what general patterns we're going to have, right? So x minus 5 times x minus 5, right? That's going to be x squared. That's going to be minus 5x. That's going to be minus 5x. That's going to be positive 25. So we're going to have x squared plus 10 x squared minus 10x plus 25. Now we see right here, oh, hey, that exactly matches that. So I know, hey, this is just factored. But that's not really satisfying. We want to find a greater rule here. And so I'll say, well, I'm gonna keep this a little abstract, right? I'm gonna go into A's and B's and figure out what the pattern is for general quadratics. So if I have something like x minus b squared and x plus b squared, what am I gonna have? Right? So we figure this out. We're gonna have x squared minus bx plus b squared, or more generally, x squared minus 2bx plus b squared. And now if we were to expand this out, we'd have x times x, or x squared, plus bx plus b squared, or x squared plus 2bx plus b squared. And we notice a general pattern. Hey, these two expansions, they really match each other except for the sign, right? If we have a negative, then our middle term is going to be negative. But if we have a positive, our middle term is going to be positive. And that's the only difference between the two. Now, where this comes incredibly useful is if you have something like, our previous problem, x squared minus 10x plus 25. I think back to it and I say, okay, 25, it's a square. It's 5 squared. And just to test this theory, I say, okay, well, that means I'm going to have something like, 5. But am I going to have it positive or negative? Well, I look at that middle term and I say, that middle term is negative. So I know that I'm going to have, x minus 5. And if I really want to confirm it, I can just take that negative 5, multiply it by 2, or take that 5 and multiply it by 2, and sure enough, I will get negative 10. I will get negative 10, so I know, yep, that's the right factorization. I've got it down good. Now, finally, we can apply this to even more complex quadratics, and ones with a term on the x squared. And that may seem scary, but it's actually extraordinarily helpful. If we have something like 16x squared, actually let's do a smaller number. Let's say 4x squared minus 12x plus 9. Now, we see that we have two perfect squares. We have 4 and we have 9. We both know that these are perfect squares, right? 4 is 2 squared and 9 is 3 squared. So we might say, okay, well, what if we took our standard, x minus b squared, but we said, hey, what if we had another one attached there? What would that be like? So we're actually going to go ahead and we're going to do this expansion and see what we have. So we have something like, I don't know, let's say ax minus b squared, right? That's ax minus b times ax minus b. And the reason I say minus b is because that negative there gives us an inkling, right? It might be, a negative situation like it was with standard x. We don't know that for sure. We're going to find that out, but it just gives us an inkling that might be true. So, but let's test that. We multiply these together, we get a squared x squared. On that we get minus axb. Multiply that we get minus abx. Minus abx minus s. When we multiply these together, we get positive b squared. So we notice, hey, all told, we get a squared x squared minus 2ab x plus b squared. And now, if we wanted to do the positive version, we would just change the signs, right? That becomes, abx instead of negative abx, and it becomes abx instead of negative abx. So the positive version would have us have positive 2abx. And now, this example, we can say, okay, so 2 is going to be my a, 3 is going to be my b, so I have 2x plus 3 squared. Now, if I just wanted to check my work, I could do the expansion. So 2x plus 3 times 2x plus 3, that's 4x. That's 6x plus 6x. Oh, sorry, minus 3. Because this is negative, so we know we're going to be following the negative pattern. So we're going to have negative 6x and negative 6x, and that's 9. So 4x squared minus 12x plus 9. And this is our original equation, so we're like, yep, this factoring works, right? And that's how we can use squares to do really, really nice things with quadratics and make our life a whole lot easier. You won't have to do any complicated guessing and checking or bring out the big quadratic formula. We can just go here, search for squares, find them, and we immediately know what the format of our factor solution will be. I hope you find this helpful, and I hope you have a great day.